Hello guys, in the last session we have discussed the same circuit in time domain. Now in this session we are going to discuss this same circuit in frequency domain. Let's analyze the circuit in frequency domain. First of all, we'll try to understand the capacitor. Capacitor impedance can be written as 1 by SC, where S is j omega, which is a frequency component, and C is the capacitance. This is the impedance of the capacitor. If we observe for omega is equal to 0 frequency, the capacitor will act as capacitor impedance can be 1 by SC. 1 by 0 into C is 0. It is infinite. So for omega is equal to 0, the capacitor will act as infinite impedance means open circuit. So capacitor will act as open circuit. For omega is equal to infinite, for high frequency, capacitor's impedance will be 1 by infinite. That can be 0. So it will be acting as short circuit. What this implies? This implies for low frequencies, capacitor is open circuited, and for higher frequencies, capacitor is short circuit. Let's do the same thing with the circuit. Circuit at omega is equal to 0. How it will be here? So we have resistor and the capacitor will act as for 0 frequency. It will be acting as open circuit. Everything else will be the same. So this 1 ampere current will flow in this path. Here it will be 0 amperes. 1 ampere will go in this way. That's a good thing. And at omega is equal to very high frequency, the circuit will be as usual. And what about the capacitor? Yes, the capacitor can be short circuited. If it is short circuited, the 1 ampere current completely will flow through this path. In this path, it will be 0 ampere since this is low resistance path. So for higher frequencies, capacitor's impedance will very low, and for lower frequencies, capacitor's impedance will be very high. So if you draw the frequency response of this circuit, if this is omega axis, let's say this is our output. What is the output for omega is equal to 0? Output is R into 1 ampere. It is R volt. After this, what is the output? It is the voltage drop here is, since the R is 0, 0 into current flowing is 1 ampere, so it will be 0 volt. So this can be something here and it is going to 0. Actually, this can be written like this. This is the location of pole. What is the location of pole? How we will calculate the pole? The location of pole can be, earlier we have discussed in time domain about tau. Tau is RC. Since this resistance, if you draw for calculating tau for equivalent R equivalent, we have to make the current source as open circuit and voltage source as short circuit. This is the ends of the capacitor. If you see from here, the equivalent resistance will be, since this is open circuited, you don't need to consider this resistance. So it will be R equivalent is equal to R. R equivalent is equal to R. C equivalent is equal to C only. So tau is RC. So the pole also will be 1 by tau. So the location of pole is 1 by tau here. This is, maybe you can write normally as magnitude R. Usually this is simple magnitude I am writing. If you write mod magnitude, you can do it is like this can be 20 log of R. This is also okay. So just for understanding intuitively, see this will be 1 by RC. This is the location of pole. How we will intuitively justify these statements? Let's say for lower frequencies, what are the components that will be in the circuit? For lower frequencies, the resistor and capacitor and these are there, resistor and capacitor. The omega is equal to 0. The impedance of this capacitor is very much high and this resistor is low, since it is zero frequency. At low frequency, the capacitor impedance will be very high. If two impedances are in parallel, the lower impedance one will be dominating. So this equivalent can be written as resistor with resistor, two resistors. As frequency increases, as omega increases. Earlier, this is open circuit, since it is 1 by SC. As S increases, it keep on tending to reducing the impedance of the capacitor. At one point, the impedance of this R and C will become equal. At one point, ZR will be equal to ZC, such that ZR is equal to R and ZC is 1 by SC. That frequency is given by 1 by SC. At this frequency, the impedance of capacitor will also matters. So this is the frequency of, means at this frequency, if you see carefully, this impedance and this impedance are equal. Both impedances are equal. That's what I did here. Both impedances are equal. So the voltage drop here will be off time. So that's what we will represent in the Bode plot also. In this Bode plot, this is the location of pole 1 by RC. Means at the point the impedances are equal, that is the point where it will give the pole. After, if omega is keep on increasing, this impedance will start going down and the equivalent will keep on reducing and it will give only the capacitor impedance only.